I'm Dr. Ian McCullough of Johns Hopkins University. This is a short lecture on matrix algebra. The objective of this lecture is to cover basics of matrix algebra to enable network analysis. We will cover some basic definitions, the dimensions of a matrix, addition, subtraction, and multiplication, and the transpose. A matrix is a collection of numbers organized into rows or columns. In this matrix, you see row 1 is 3, 8, 2, row 2 is 5, 0, negative 1, column 1 is 3, 5, column 2, 8, 0, column 3, 2, negative 1. We typically place the elements of a matrix into square brackets, and we'll use a capital letter to represent the matrix as a whole. So this is matrix A. We refer to matrix A as a 2 by 3 matrix, referring to 2 rows and 3 columns. The elements of the matrix are often use a lowercase letter to represent each element, and the element A is indexed by the row and then the column. So for row 1, column 1, we have little a sub 1, 1. For row 1, column 2, we have little a sub 1, 2, and so forth. A vector is a special type of matrix that has either a row or a column. So matrix B is a column vector, meaning that it just has a single column of elements. Vector C is a row vector, meaning that it has a single row of elements. And we keep the numbering for the index consistent. So you'll see 1, 2, 3 is being incremented here along the row index, and here we have 1, 2, 3 being implemented along the column, for each column. A scalar is basically just a single number. It's also represented by a lowercase letter, typically without the indices. We'll denote vectors by bold, lowercase letters, and matrices with more than one row or more than one column by a bold uppercase letter. So a square matrix has the same number of rows and columns. So matrix A here in this example is square. It has 2 rows and 2 columns. Matrix B is not, because although it has 2 columns, it has 3 rows. A symmetric matrix is a square matrix, and it's where the element ij equals ji. So think about that for a minute. What it means here is that ij here would be row 1, column 2. So that would mean that to be symmetric, column 1, row 2, right? Or 2, 1 instead of 1, 2, would be the same element. So you'll see this visually that the element here is now here. This entire row is the same as this entire column. This entire row is the same as this entire column, and this entire row is the same as this entire column. So this becomes a symmetric matrix. If we look over here at matrix B, it is not symmetric. When we look at element 1, 2, it is not the same as element 2, 1. A diagonal matrix is a symmetric matrix where all of the off-diagonal elements are 0. So if you look at this going from element 1, 1 all the way down to element 3, 3 here, along this diagonal area right here, these have the entries. Everything that's off this diagonal is zeros. And you may see why this is important when we do some multiplication. Now note, it's not any diagonal, right? So if this was the diagonal going from the upper right down to the lower left, that would not be a diagonal matrix. We are referring to a special matrix where we're going from the upper left to the lower right, has elements or entries, and all of the other entries, elements of the matrix, are 0. An identity matrix is a diagonal matrix where there are ones and only ones in the diagonal, and all of the other elements are 0. We refer to the identity matrix as a capital letter I. We're now moving into addition and subtraction. So the first things we have to do before we can add matrices is something called dimensional analysis. Now, dimensional analysis sounds really cool, but it's quite simply making sure that you can perform whatever the intended matrix operation is. So in order to conduct addition and subtraction, the two matrices that you're adding have to have the same dimensions, the same number of rows and the same number of columns. Since you're looking at the dimensions of the matrix, that's why we call it dimensional analysis. So in order to add matrix A and B, you have to make sure that the dimensions of matrix A, in this case 2, 3, is the same as matrix B, 2, 3, and the resulting matrix will have those dimensions, 2, 3. In order to conduct the operation, you're simply taking for the new element here R, ij, you're simply adding the corresponding element in matrix A to the corresponding element in matrix B. So if we look here and see, here's the addition of 1, 8 is going to equal 9. Okay, a 9 and a negative 4 is 5. A negative 2 and a 3 is 1. And so forth for the second row. Now, I'll tell you, subtraction is really no different. You're just essentially distributing the minus sign through the matrix and then adding. So here's an example that I would like you to pause the video, conduct this operation, and then check your answer. I'm assuming you have paused the video. You have completed the operation, and you're now here to check your answer. If you have got the wrong answer, then I ask that you rewind the video and review the section that we have just covered. We're now moving on to matrix multiplication, which gets a little more tricky. There are several rules for multiplication. The first refers to multiplication between a matrix and a scalar. And so here, when you have a scalar A, it is multiplied by every element in the matrix. So if you look at the below operation here, where we have 8 times matrix B here, which is 2, 6, 3, 7, we're going to simply multiply 8 by every element in this matrix. So 8 times 2 becomes 16, 8 times 6 becomes 48, 24, and 56. For dimensional analysis in multiplication, it gets a little more tricky. If we're going to do two matrices, A and B, we're going to, again, do dimensional analysis, but here we have to look at the dimensions, right? So if we have R by C for rows by columns, and S by D, referring to rows and columns again, but we need different letters because we can't use R and C again. What we need to make sure is that the columns of the matrix on the left and the rows of the matrix on the right are the same. This is referred to as conformable. So are the matrices conformable? They are if the columns of the left and the rows of the right correspond. You'll see why this is true when we go through the operation for matrix multiplication, but this is the first step, is making sure that you can actually perform the operation. The resulting matrix will have the dimensions of the rows of the matrix on the left and the columns of the matrix on the right. And what you might be realizing here is that A times B may not be the same as B times A, like in typical multiplication. In fact, A times B might be possible, whereas B times A is not a allowed operation at all. So let's look at these two matrices. What are the dimensions? Pause the video for a minute and write them down. Make sure you understand the concept. Assuming you've jotted them down. The dimensions of the matrix on the left are 1 row, 3 columns, 1 by 3. The dimensions of the matrix on the right are 3 by 1. We have 1 by 3, 3 by 1, so the columns on the left are the same as the rows on the right, so this is an allowed operation. So the row vector must have as many columns as the column vector has rows. So this here on the left is an allowed operation, but the one on the right is not, because here we have 3 columns and we have 4 rows. They are not conformable. We can't just make it simple and say multiplication, although some software packages do. We call this the dot product. And so the way you conduct a dot product is you take the elements, you multiply them together. So here we're using I to refer to the elements of both the row vector and the column vector. And the resulting value is going to be, for each of these indices, we're going to have the element in A times the element in B, and then we're going to add them together. So what you'll see here is the numbers outside the parentheses are referring to the row vector. So you have 9, 5, and 1, 9, 5, and 1. And inside the parentheses will refer to the column vector, 1, 3, and 5, 1, 3, and 5. So when we multiply those together, you get 9, 15, and 5. We add them all together to get 29. So yes, the result of a row vector times a column vector is going to be a scalar number. Now let's say we want to find the dot product of A, B. So now this is a matrix of 2 rows, 3 columns. B is 3 columns, 2 rows. So is that conformable? Yes, because the number of columns 3 matches the number of rows 3. The resulting matrix is going to have 2 rows and 2 columns. So what we are going to do for element 1, 1 of the resulting matrix, row 1, column 1, we are going to take the first row of the left matrix here, 2, 8, 1, times the first column. So element 1, 1 is going to be row 1, column 1. So we have the 281, 196. We're going to multiply that out and get a scalar number of 80. For row 1, column 2, we're going to use row 1 on the left, column 2 on the right. So you're going to have 281 again, but now you're going to use 7 minus 2 and 3. You get a different scalar number. We complete that now. Row 2, column 1 is going to use the second row of the matrix on the left and the first column of the matrix on the right. So now you begin to see why we need to have these things conformable, because if I'm going to have an operation here where I have 3 columns on the left and 3 rows on the right, I need to have the same number in order to match these pairs up to complete the operation. If I had a 4th element down here, I wouldn't have anything to multiply it by. The operation loses its meaning. So the resulting dimensional analysis of knowing it's 2, 2 helps me kind of iterate through what elements of R do I need to calculate to make sure I've done all of the necessary operations. So when I put all of those elements, row 1, 1, R11, R12, R21, R22, into the resulting matrix, I have my result of the matrix multiplication. So let's just go through this again. For matrix A is a 2 by 3 matrix. Matrix B is a 3 by 2 matrix. I do the dimensional analysis to see that the number of columns on the left matches the number of rows on the right, so I can do the operations. The resulting matrix is going to be 2 by 2, so I create my bracket here for 2 by 2. And then I look at each element in the matrix, and I know that this is going to be element 1, 1, so I have to use row 1 on the left, column 1 on the right. For something like this, row 1 on the left, column 2 on the right. And so I do those operations, and that allows me to calculate my matrix multiplication. I'm going to ask you to think about this. Is this operation possible? Why or why not? Take a moment, pause the video, and jot down your response. I'm assuming you've taken a moment to jot down your response. Now let's look at this. What is the dimensional analysis? We have a 3 by 1 on the right, a 1 by 2. Is it conformable? The answer, of course, is yes, because the number of columns on the left match the number of rows on the right. The resulting matrix is now going to be 3 by 2. When we conduct that operation, element 1, 1 is going to be row 1, column 1, negative 24. Element 1, 2 is going to be row 1, column 2, negative 6. Row 2, column 1 is going to be row 2, column 1, and so on. The transpose of a matrix is denoted by a little prime symbol, or it's often referred to with an uppercase T for the transpose. When we conduct a transpose, the first row of the matrix becomes the first column, and the second row of the matrix becomes the second column. So 2, 8, negative 1 becomes the first column, 2, 8, negative 1. The second row, 3, 6, 4, becomes the second column, 3, 6, 4. We're now going to go through a short application with networks. If I'm going to take this example from forensics. So if I take a symbol here referring to a bunch of individuals, and I have explosions that have occurred, and so I go to those explosive sites and I take fingerprints off of the explosive materials, I can associate certain individuals to certain events. So in this case, every person has been involved in 2 events, as referred to by the checks. I can represent that as a network that has 5 rows and 4 columns, or a 5 by 4 network, which I'm going to refer to as X. So a matrix can always be multiplied by its transpose, because keep in mind we're taking the rows become columns, columns become rows. So now when I have a matrix X of dimensions row by column, the transpose is going to be the number of columns by the number of rows, right? Those switch. And so what that allows me to do is construct a network. The resulting network is going to be the rows of the matrix on the left times or by the columns of the matrix on the right, which, because we did the transpose, are the same as the rows on the left. So it allows me to take this forensic information and collapse it into a social network. And the meaning here is who has constructed bombs together, or who has participated in the events together. And what it allows me to do is it says, hey, this person can skip to either of these 2 events. Now who can they be connected to? Well, anybody that's connected to either of these 2 events, right? So this guy can be connected to any of these 3 people, to include himself. This guy, the same group of people. The same thing goes for these people, and you'll see that this middle node here is the only one that kind of spans the 2 clusters. That would be the node here in the middle. And that allows me to conduct network analysis to determine who is the central actor in this network. Now I'm going to ask you to go to the matrix algebra practice problems in your lesson and practice several of the problems that are given there to gain proficiency in matrix addition, subtraction, multiplication, and calculating a transpose. Thank you for listening to this short lecture on matrix algebra. Please email me if you have any additional questions. This is Dr. Ian McCullough of Johns Hopkins University.